So finally, let's look at problem number 2. In the exercises where we are asked to verify that the divergence theorem is true for the case given in problem number 2. And that case is that the vector field is x squared I plus x y j plus zk. And E is the solid bounded by the paraboloid. Z equals 4 minus x squared minus y squared and the xy plane. Okay, so paraboloid is opening downwards, and it's pretty bad. Like so, roughly. Let's see, even though we're not gonna do the whole thing right now, let's go ahead and label the different parts. Let's call the base S1, and let's call these sides here the lateral, as it were, surface S2. So when we're doing the part directly evaluating the flux, we'll break it up into those two integrals. All right. So what we have to show is that the double integral over S, where S is the union of S1 and S2, f dot ds, is the triple integral over the region bounded by S of the divergence of the vector field. So let's compute the divergence. So we'll do, part 1 is to just directly compute the divergence. Divergence of F is 2x plus x plus 1, so that's 3x plus 1. And we need to integrate 3x plus 1 over the interior of this region. Again, this is cylindrical coordinates. We'll go from the base up to the point directly above each point on the base, and that's a point on this surface. So S2 is the z equals, 4 minus x squared minus y squared. Okay, so, and then this is not the unit circle, I guess, but it is the, if you set z equal to 0, you get x squared plus y squared equal to 4. So that's r equals 2. So then cylindrical coordinates are theta goes 0 to 2 pi, r goes 0 to 2, z goes 0 up to 4 minus x squared minus y squared, but that's 4 minus r squared because this is 4 minus x squared plus y squared, which is 4 minus r squared. And then we're integrating 3x plus 1. So that's 3r cosine theta plus 1. And then r dz dr d theta. There are no z's here, so this is 3r cosine theta plus 1 times z integrated from 0 to 4 minus r squared. Let's see, I can throw the r in over here, and then I'll have dr d theta. Okay, so 0 to 2 pi, 0 to 2. So this is just going to be 4 minus r squared. For the purposes of multiplying this out, well, I'll go a little slower. 3r cosine theta plus 1. This then becomes times 4 minus r squared dr d theta. And I've got the r here. Let's first put the r into one of these. So 3r cosine theta plus 1. Let's make this 4r minus r cubed dr d theta. And then multiply all of this out. And we get 12r squared cosine theta minus 3r to the 4th cosine theta plus 4r minus r cubed dr d theta. Well, when you take antiderivatives of cosine, you're going to get sine. Sine evaluated at 0 and 2 pi are both 0. So these are just going to go away. And when you anti-differentiate this with respect to theta, so I'm doing the theta integral first, even though I've got it written. It's just going to give us 2 pi. So 0 to 2, 2 pi, 4r minus r cubed dr. So that's 2 pi. And if I go too quickly here, press pause and compute that integral and get 0 for it, hopefully. But these will integrate to 0. And we got 4r squared over 2 minus r cubed. I'm sorry, r to the 4th over 4, 0 to 2. 2 pi, this is 2r squared, so this is 2 times 4 minus 16 over 4. Is that right? So 2 pi times 8 minus 4 is 4, so I'm getting 8 pi. All right, that's the divergence side. So now it's up to us to integrate the flux directly. And get 8 pi, we hope. So the flux is going to break down. Remember, S is S1 union S2. So let's first do the flux of F across S1. Now, S1 is in the XY plane. So the differential of surface area doesn't give us anything new. So we will do this as F dot N dA. We don't have to put ds here because anything parallel to the XY plane gives us nothing with regards to curvature or angle or anything like that. So our N, in this case, outward flux is going to be minus K. So 0, 0, -1. And then F dot N is F dot N. So that's 0 times x squared plus 0 times xy plus -1 times z. So that's negative z. But, and we're integrating over S1 minus Z dA. But of course, on S1, Z is equal to 0. So this is minus the double integral of 0 dA, which is 0. So it all boils down to the flux of F across S2. And across S2, the surface is a function of X and Y. So that's this, and since we're doing outward or upward flux, or what amounts to upward flux in this case, our normal vector, remember, is minus z sub x minus z sub y 1. Partial with respect to x is minus 2x, but then negative of that is positive 2x. Similarly here, positive 2y, and then 1. And f dot n is, let's see here, f dot n is then 2x cubed plus 2xy squared plus z but we're integrating this over this function over the region that this function is a function of x and y over, and that's really just S1, but we're going to call that A in this case. So this is a polar integral. So we want to state z as a function of x and y. So this is 2x cubed plus 2xy squared plus 4 minus x squared minus y squared. And then we integrate this, the surface integral over S2 becomes that polar integral. So we've already gone through the details of what that looks like. Let's see. This, if I factor out a 2x, I'll just do that here, 2x, and then I would have x squared plus y squared, and then plus 4 minus x squared plus y squared, and then this is r dr d theta. So integral 0 to 2 pi, integral 0 to 2. This is 2r cosine theta times r squared plus 4 minus r squared r dr d theta. Let's see. Again, this term here is going to go away when we integrate with respect to theta. So let's integrate with respect to theta first. And this will go to 0. And then we're left with the integral from 0 to 2. R multiplies through here. This is 4r minus r cubed times 2 pi, because we're doing the d theta integral here, and this is a constant with respect to theta, so we get the 2 pi. And then dr, and this is actually exactly the same thing we had. Notice in the divergence integral, we ended up 0 to 2 pi, 4r minus r cubed dr, 0 to 2 pi, 4r minus r cubed dr. It's the same thing. It integrates to 8 pi. So, all right, so we got the same thing, thus verifying that the divergence theorem holds for that particular case. All right, so that wraps up the lectures for 16.9. The homework for 16.9 is 1 to 13 odd. And some of those, especially maybe the number 3, the verify the divergence theorem for the cylinder. It's not a short problem. It's actually one I used to cover in lecture. So we can talk about that in class if you get stuck on it. And I will see you in class before the final exam.